time. Time seems to run slower the further you look. I'm trying to wrap my brain around that idea. And thankfully, I have here someone with me who is going to help me and you understand why that would happen. He's authored two cosmology books, over 500 papers, and one of them recently was published in Nature Astronomy to find more evidence for what's called cosmological time dilation. From the University of Sydney, astrophysics professor Geraint Lewis. Thank you very much for
Hello.
being here. Welcome. Hi, how are you?
I'm good, thank you. How are you?
All right, so if we can, before we move on to cosmological time dilation, the big one, let's discuss the regular time dilation that everyone knows of. So I have a clock with me here. Okay. All right.
hmm
And I think the simplest one is probably the special relativity time dilation. So if you wanted to see this clock run slower or faster, what would you need to do?
Well, what Einstein told us is that time is a relative thing. So clock rates differ between observers dependent upon their motion. So, of course, if I've got my clock with me, I always see it run at 1 second per second. But if somebody is moving with respect to me and I compare my clock to their clock, we see the clock rates will be ticking differently. And this is, one of those consequences that Einstein came to in 1905 when he realized, that the speed of light has to be the same for everybody from Maxwell's equations. And so space and time have to be flexible to account for this. And of course, this is well tested. It is well known. It seems very strange, very counterintuitive that time should be different for different people. But that's the way the universe seems to work.
So, for me, special relativity time dilation never felt like actual time dilation. Because from my understanding, like if I'm looking at your clock, it would appear slower to me. And if you were to look at my clock, it's my clock that appears slower. Am I correct in that
That's right. That's right.
analysis?
Yes. Yeah. So often I think the way I normally like to think about this is not really about looking at somebody else's clock necessarily, because there are lots of other things that come into play. But you are right. Is that if I ask the question of how fast is your clock running with respect to mine, I would say slower, and you would see the same. So it seems to be that there's both viewpoints are equivalent, and therefore there should be really no effect, right? It looks like everything should cancel out. But the real test is not really looking at somebody's clock. The real test is having two clocks, keeping one with you, sending one off to do something, and then bringing it back and then comparing the clocks again. And what we find when we do those kinds of experiments is the amount of time that has passed on each clock is different based upon what those clocks do. And this has been tested experimentally to a very high degree, both with regards to laboratory physics, where people flew clocks around the world, and to particle interactions. There are these particles that crash into the atmosphere. They create these things called muons. And we know those muons live for roughly a millionth of a second, but we see them arriving here on the ground because their lifespan has been dilated with respect to us. Right? They seem to last longer because their clocks tick slower. So it's the way the universe works. It's there.
So correct me if I'm wrong. So, do you need general relativity for like to see a difference in a clock? If I get in an airplane, for example, and then land, is that general relativity or is that special relativity that's causing actual difference in time?
Well, so I try to be very, very careful here. So I try not to separate general and special relativity into two theories, because they're not. One is a subset of the other, right? So the issue about being on the Earth and flying a clock around the Earth is that you do have to worry about the gravitational field, the fact that you have gravity there. And anytime you have gravity at play, you are playing in the realm of general relativity. Special relativity only holds in truly empty space with no gravitational fields. But here on Earth, the gravitational field is weak enough that we can normally avoid most of those effects. But the experiments that people did, yeah, you do have to think about the fact that if I leave one clock at home and another clock flies around the world and is up in the air at a few kilometers, the gravitational fields are slightly different. And that gives you an additional contribution to the overall time dilation. So you've got that motion plus the fact that you're at a different location in a gravitational field.
So, I mean, from my understanding, like to have like a difference between two clocks, one, for example, it needs to be in a warped gravitational field. Like if I'm next to a black hole, for example, it would cause more time dilation. Is that correct?
Yes, yes. So again, the way you can think about it, as you said, is that gravity is a manifestation of the curvature of space and time. And so as you're near a black hole, then clock rates tick differently to at other places in the universe. So there's a simple way of building a time machine to go into the future, right? So all you need to do is find the black hole, fly to the black hole and just hang out near the center and then come back out again. And we saw this in Interstellar, right? You go near a black hole in Interstellar, you're
Yeah.
down on the surface of the planet for just, a matter of hours, and you come back up and your spaceship mate has aged decades in the time that you've been down near the black hole. So yeah, it would be there's that what's known as gravitational time dilation when you have strong gravitational fields.
Now, to me, that's kind of intuitive. Like something warps space time, and that causes time dilation. The one that I always struggle with is if you accelerate and then decelerate, somehow whoever has accelerated their clock would have ran slower than someone who's not near a gravitational field. Why would acceleration cause time dilation? Am I warping space? Is that what's happening?
No. So you can treat acceleration purely within special relativity. So you don't need to warp space at all. So the real thing is it's not really the acceleration that matters. What matters is the fact that you've put one clock in motion with respect to the other. And the key point in special relativity is that to bring the clock back, for you to do the comparison, which is what the classic twin paradox experiment or idea is all about, is that you have to change that reference frame, right? So you send your clock going outwards and it's going at some velocity, and then you bring it back and it's coming towards you at this velocity. To get from one to the other, you need to change your basic inertial frame, as it says, and it's that's the key point, right? It's the fact that you have to. The way I like to tell my students is it's this, right? So generally in special relativity, if you've got 2 points in space and time and you want to connect them, then the longest distance between them, which is the time experience, is a straight line. Okay? So on the twin paradox, the person who stays at home, they're the one that experiences the most time. Any path that you connect 2 points that has a kink in it, those paths are always shorter. So it's the act of putting a kink in your path. That's the key point that gives you the fact that the time experience is less for the person who goes out and comes back. They've got to put a kink in the path to come back.
Ah, okay. All right. So it's like taking a detour. So,
Yeah.
I mean, this is the kind of time dilation I'm kind of familiar with. But let's move on to the big question then. What is cosmological time dilation? So, how is it different than the kind of time dilation we talked about?
Well,
What is it and how is it different?
okay. So it's different but the same, right? So in some level, because
Okay.
it's not like we need to do a separate set of mathematics to work out cosmological time dilation. We do exactly the same things as we did for what we spoke about with a black hole, but this time now talking about the gravitational field of the universe. So in cosmology, of course, we've got these mathematics, the Friedmann-Robinson-Walker metric, etc., that allows us to talk about the space-time of the universe as the universe expands. So we have this beautiful set of mathematics, and I can ask myself the question, what happens if I compare a clock here to a clock over there? And of course, in the cosmological sense, what I'm talking about there is, of course, is if I've got my clock here and I'm observing a clock in the universe, the light from that clock set out a certain amount of time ago, right? Because the universe is expanding, the speed of light is finite. So it might be a year, or it might be a million years, or it might be 10 billion years that light is traveling. And the key thing is that means that the space time in the universe today, when I receive that signal, is different to the space time in the universe when that signal was sent out. In the same way as we said, right, near the black hole, you've got a stronger gravitational pull near the black hole, less of a pull outside, so the curvature of space is different. Here, what we're saying is that the curvature of space when that light was emitted is different to the curvature of space today. And one of the consequences of that is you end up with a time dilation. You end up with this realization is that if you could fill the universe with clocks and you could see those clocks out into infinite space, as you look out at the clocks, of course, firstly, they would look smaller because they're further away. And then secondly, we would see the clocks run more slowly compared to my clock today. And the further back I look, the slower and slower that clock appears to tick. And in fact, in theory, if I could see all the way back to the Big Bang, the Big Bang would be frozen. There would be no time passing at that point. There would be an infinite amount of time dilation.
Interesting. So if I were to see some kind of event that takes some time to happen, am I going to see it in slow motion if it's sufficiently farther away?
Absolutely. So this was something that was realized back in the 1920s and 1930s, and they already realized the kind of object that people would want to look at. And they predicted that a particular kind of exploding star, a supernova, right? It's a star that brightens very quickly. It's an explosion, but then fades away over a certain period of time. And it took a lot of work, most of the 20th century actually, for people to realize is that they could find essentially identical explosions. The problem is not each supernova has its own peculiarities. They're all slightly different. And if you're trying to time something, you can't have your individual clocks doing different things. You want them all to be doing the same thing. So there was a particular kind of supernova known as a supernova type 1a. Again, a very boring name. Sorry about that, because it's just a classification. But it was
I love it. Like, it's just the supernova.
Yeah. So it was realized is that in the local universe, these things got bright and then faded away over a period of, say, 3 weeks, right? And so throughout the early 2000s, people were looking at these supernova out into the universe, looking, let's say, roughly halfway back to the Big Bang, and they were seeing how long did it take for these supernova to brighten and fade, brighten and fade, brighten and fade. And what they find, of course, is that the more distant supernova they see, the longer it takes to go through this cycle of brightening and fading. So the most distant supernova they saw actually took twice as long to do that as a supernova that we see in the local universe.
Interesting. How far away were those supernovae?
They were roughly about 5 billion light years.
5 billion light years. So that was in the early 2000s. So was that the first evidence for cosmological time dilation?
Yes. So that was the first robust evidence. It's one of those. That wasn't their main mission. Their main mission was to look at the expansion of the universe, and it was from these experiments that they discovered dark energy and all that kind of stuff. But as a sideline, they found that they could also test for cosmological time dilation. And so they showed that at least out until around 5 billion light years, the universe was behaving just as you'd expect, right? We were seeing these clocks tick at this slower rate.
And from my understanding, from your latest study, you've basically found evidence that it's happening even farther out. Am I correct in my assumption?
Yes. So I mean,
so how have you found that?
Okay, so I'm going to wind back very slightly, right? So I've always been intrigued by this. There's
Sure.
a particular mystery, right? Uh, Now, supernova are not the only variable sources in the universe. There are other variable sources, and some of the most noticeable are these objects called quasars. Now, quasars were discovered in the 1960s, and people have come to realize that they are supermassive black holes, so black holes with masses of millions to billions of times the mass of the sun, and they have material swirling around them at close to the speed of light. So that material gets very hot, glows very brightly. And some of the most distant objects that we can see in the universe are these objects called quasars. And because that disk of material, you can imagine it's a really bubbling, sort of happening kind of place. The output from these quasars varies. So they get brighter and fainter, brighter and fainter, brighter and fainter.
Just like supernovae.
Yes, just like supernova, but um, quasars are very irregular. So unlike supernova, which goes
Ah,
flash and then fade, they vary more like the stock market, right? So, up and down kind of thing. So it was quite clear that these objects they have variability, and so people said, "Oh, well, we should expect to see this cosmological time dilation in these quasars." And they went out looking for it, and a group of people have searched for this over the decades, and they failed to find it. And in fact, there was a colleague of mine, Mike Hawkins at the University of Edinburgh, who's been looking into this since the early 1990s. He had this big sample of quasars that had been observed for 30 years using photographic plates, and he had their variability. And he did a bunch of statistical analysis to try and reveal how similar or different the nearby quasars are to the more distant quasars, right? I.e., we expect the more distant ones to run more slowly. And he failed to find any difference. So it really was annoying, right? These things should show this signal, and whilst I think many astronomers thought that maybe that there's not enough data yet, or we don't understand quasars properly, or something like that, some segments of people, normally on the internet in dark places, grab hold of this idea and sort of started saying, oh, clearly the Big Bang is wrong, right? We don't see this cosmological time dilation. So therefore, the predictions that people have about the universe, they must be wrong. It's all based on incorrect assumptions, etc. So this is one thing that's bothered me. This signal should be there, and nobody was seeing it. And then at the end of last year, there was a new sample of quasars published. So these were roughly 200 quasars. They were observed originally in what's known as the Sloan Digital Sky Survey, which was this really big project which maps the sky in really high quality, but then focused on a narrow piece where they identified these quasars. And the astronomers had gone back over 20 years and collected data on the variability of these quasars. So it was this brand new data set, and they had a lot more data than had previously been collected. And we thought that we understood the statistics of quasar variability, right? It's not that we can predict whether it's going to go up or go down, but on some time scale, there is some characteristic variations that go on in the quasar light curve. And so I decided to take that sample and basically analyze it. And so I had to do a few things. I had that characteristic variability timescale, so that was in there. But the big problem is that quasars come in different kinds. Just like supernova, some can be brighter, some can be fainter. It's the same with quasars, but some can be 1,000 times brighter than another one. And so if you imagine you've got these objects, they've got lots of similarities, but maybe the one that's much bigger has a lot more activity and so will vary differently to the ones which have less massive black holes. And similarly, the accretion disk, this disk of material, right, which is swirling around, in the center, it's exceedingly hot, hundreds of thousands of degrees, but it cools down towards the edge. So you can imagine the center is all X-rays and gamma rays, and then it's kind of blue, and then it's kind of red, and then it goes into the infrared, the further out you go. And
It's
when
all
we
over the
look
place.
at it's all over the place, yes. Quasars emit energy right across the electromagnetic spectrum. But the problem is that when we observe a quasar, imagine, so normally we put a filter on our telescope and we collect how much red light, how much green light, how much blue light. Then if I'm looking at quasars, and let's imagine I'm just looking at them through a green filter. So green light on Earth, of course, is somewhere between red and blue. But the light that has come from those quasars, that's been affected by the expansion of the universe. And its wavelengths have been stretched. So some of the quasars I'm looking at, they might be emitting actually, maybe the nearby ones, I'm seeing them in green light. That's the color that they are. But the ones further away, they emitted their light in the blue, and it's been stretched, and I'm now seeing it as green light. And even more further, they could be emitting their radiation in the ultraviolet, and their light has traveled and stretched and now arrives at my telescope as green light. So I have to worry about exactly where the emission is coming from in terms of, is it coming from close by, sent to the near to the black hole, or is it further away, etc. So this sample allowed me to basically group quasars together. So I could put the most luminous quasars observed in the ultraviolet together and the least luminous quasars observed in red light together, etc. So I could basically compare like with like. And then once I had done that, then I basically looked at their variability, and my working hypothesis is that the variability of all these objects is the same, except for the influence of this cosmological time dilation, right? So if you imagine I've got a bunch of quasars, they're all varying, and I'm saying they all should behave the same, but the ones which I'm seeing from larger distance, I should expect them to be dilated, that their time should be slower due to the expansion of the universe. And so that's the kind of test that I did, and I went through and I did the full hypothesis test and all the statistics that nobody ever wants to actually talk about, but it's the key of doing science. And that's the signal that came out. The signal that came out is that this sample, there is a signal across it, and that signal is precisely what is expected from the cosmological equations when it comes to time dilation. We're seeing precisely the slowing down of the distant universe as the equations predict.
So from my understanding, quasars were thought of as not good clocks because they vary too much.
Mm-hmm.
And we had like a larger sample size now, and that basically allowed us to figure out that cosmological time dilation has been happening even earlier, like actual evidence to that. Am I correct?
Yes. So what, again, one of the nice things is this sample of quasars, because they're so much brighter than supernova, we actually see them back over 90% the age of the universe. So we know more almost double the distance that the supernova had measured this effect over. And that meant that the most distant quasars we were seeing, their time dilation, we were seeing them run basically 5 times slower than nearby quasars.
How far away are these quasars? How old are they?
So we're seeing them. The light was emitted about, the most distant ones, about 11 billion years ago.
11 billion years. So they'd be like 2 billion-ish years old,
Yes.
Something like that.
Yes.
And if maybe I'm oversimplifying, if I were to have a very powerful telescope, much more powerful than anything we have, and I were to observe that quasar, it would seem like it's running 5 times slower.
That's right. But the problem that you're going to have is the variability is kind of complicated, and you don't have anything to grasp hold of to tell you that it's looking like it's running slower, right? What you really want is for that quasar to actually hold up a clock just like you are holding, and then you would see that as 5 hours tick by on your clock, only 1 hour will tick by on the quasar.
So I need like a reference, like I need a quasar outside the solar system. And that's going to give me a reference for how fast things are moving.
Well, again, look, quasars are, like I said, like the stock market. So you predicting what goes up and goes down is not easy to do. But even the stock market, of course, has time scales in it, right? So, you can statistically analyze the stock market, and there will be periods of it doing this and then it settles down. And then, so there will be time scales in there. That's the only way that you can pick this out, is by statistically identifying the time scales. It's annoying because what you want is for the universe just to have a nice clock that ticks back and forth, that you can say, oh, I can see this running slowly. But it doesn't do that, right? You have to work hard to find the tick.
All right. So you need many. You can't just have a sample of one. I need like 200 quasars outside Earth, and
Well,
then another 200
yes.
at each distance to have a very fine scale.
So like everything, right? This is a data limited problem. So to do this work, right? Hundreds of astronomers had to collect data on these 200 quasars for 20 years. Okay, so it's not something that you can go out and just do tonight. Things are going to change in the near future, though, because what's happening is we have got lots of new telescopes coming online at the moment, and they're really going to change things. So we have the Vera Rubin Observatory, which is coming online very shortly, and its telescope's goal is to essentially map the sky over and over and over and over again. So what it's interested in, of course, are the variable sources. How are things changing? And so we will now start to collect this kind of quasar data for not 200, but 200,000 quasars. And so what we really want to do is then really see this signal out over, all the way back as far as we can go. And in fact, we'll see more than 200,000. We'll see millions and millions of quasars. We're going to be, like many areas, we're going to be completely swamped by the available data.
All right. So I mean, if you can just try and explain, I never quite understood why light with redshift, that's what you're measuring, like how much it elongates the wavelength of photons as they reach us, right? Why would that happen? Is it because of the expansion of the universe, or is there something else going on?
So look, there is a hand wavy picture that people like to do, but I'll do it. But I'm not a fan of this. But essentially, you've got your wavelength of light,
Okay.
and the story that we tell people is that as space expands, then the wavelength of light expands proportionally with it, right? So the wavelength gets longer. But that's not really what happens, because that sort of makes it sound like somehow space grabbed hold of the light and stretched the light. But that's not really what happened. It's in a similar vein to the time dilation kind of argument. It's because space-time out there was different to space-time here. Okay, so you get a redshifting effect if you have that difference in space-time. Similarly, with the black hole example that you spoke about earlier on, if you're close to a black hole and I'm far away, and you send a blue piece of light out to me, as it comes out of the black hole, it arrives at me, it appears to be red, right? Because the space-time you're in and the space-time I'm in are different. So it's a difference in space-time, but there's another way of thinking about it that I like. So let's think about it this way. How do you create light, right? And light comes from oscillating electrons. You can think about it that way, right? We know about transitions, but if you take an electron and you make it oscillate, okay, then what you get is you produce light with this frequency, and because the speed of light is a constant, then you get a certain wavelength. So everyone's kind of happy with that picture. Yeah. Now let's think about what we already said with time dilation. Okay. So if I could imagine that I look at that distant source and I could see the electrons oscillate. Okay. So here on Earth, I can see it doing this, but out there in the universe, it's now doing this. Okay. So that's how it appears to me. So that oscillation, right, is now at a lower frequency, right? I see a lower frequency of that oscillation, which must mean that the associated light that I see emitted has a longer wavelength. Does that picture sort of make sense?
I think from what I understood, like depending on how close you are to the um, after light was emitted after the Big Bang, like the closer it is to 13.7 billion light years, the more disproportionately it's going to get elongated. It's not like a ratio. It's not like a fixed ratio.
No,
It's exponential. Is it?
So yeah, so essentially, the way the best way to think about it is that the redshift we observe is proportional to the size of the universe when the photon was emitted. Well, it's actually 1 over the size, right? So if you imagine that we're here today, so the universe has a certain scale today. If we go back to when the universe was half the size it is now, i.e., everything was closer together by a factor of 2, okay? That would mean that light that was emitted from that time, by the time it's reached me, that has been redshifted by a factor of 2, okay? If I go back to a time when things were closer again, they were only a tenth the separation that we see objects now. The light that's emitted then, by the time it reaches me, that's been stretched by a factor of 10. So it's always the ratio of sort of like the size of the universe today to the size of the universe when the light was emitted that basically sets the size of the redshift. And as you go back all the way towards the Big Bang, of course, with the Big Bang, the distances between objects goes to 0. So 1 over 0 goes to infinity. So there's an infinite redshift from the moment of the Big Bang.
I want to play a clip real quick, and then I'm going to have a follow-up question. It has to do with what we just discussed. So I'm just going to share my screen 1 second real quick. All right. This is from this one. All right. Can you see it? I haven't played it yet.
Yep.
Right. 3, 2, 1.
Is it possible that in the future we'll be able to see past 13.8 billion years?
Not with light, because the universe was opaque to light. If you look at the Andromeda galaxy, it's about 2 million light years away. It's the most distant object you can see with the naked eye. As you look further out into the universe to more and more distant galaxies, you're looking further back in time, because you look at something that's 1 billion light years away, then the light took 1 billion years to get to us. So you see it as it was 1 billion years in the past. And we can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang. So we can look to light that began its journey before there were galaxies. And that's the oldest light in the universe, which is something called the cosmic microwave background radiation, which is, by the way, one of the pieces of evidence when people say, I don't believe in the Big Bang. The answer is, well, you can see it just there. You can see it. We have pictures of it.
Is it possible?
So my question is, the universe is around 13.8 billion years old. And the furthest point we can see is around 46 billion light years. So the light that's redshifted from around the cosmic microwave background until it gets to us, is that light 13.8 billion light years old, or because of how close it is to the cosmic microwave background radiation and how far it traveled, it's effectively older than that? What do you think of that?
The answer is that light is about 13.8 billion years old. So you have to be very careful when talking about the universe. So as you said, that the universe is 46 billion light years across, right? So that number applies to today, right? So if I could freeze the universe now and ask where are the most distant objects in the observable universe today, they are whatever the number is, 46 billion light years across, I can never remember the numbers. But remember that when that light was emitted, everything in the universe was much closer together, right? So that light was emitted from a point 13.8 billion years ago, and it's been traveling towards us. But as the light has been traveling towards us, the object that emitted the light has been moving away. Okay, so the light gets to us today, and the object is now. I just realized you probably can't actually see where my hands are, right? So here's the object. Light's emitted. It comes towards us. This object is moving away. So light arrives today. The object today, and the object is out there at the edge of the observable universe, whatever it is, and that is that number, which is 46 billion light years. But the light has been traveling for almost 13.8 billion years.
All right. So let's say I'm going to ask you something no scientist should ever be asked. I'm going to ask you to speculate, if you don't mind.
Okay. Oh, I like speculation. Go for it.
All right. So in your study, you basically measured at around 2 billion light years it was 2 billion light years after the Big Bang. If we were to observe events there, quasars specifically, they would be running around 5 times slower. Let's say the universe is now double the age of it is today. Let's say it's, how much is that? 27 billion it's 27 billion years old. If I were to look at those same quasars now, how much would you estimate that I would be seeing them? How fast are they moving, evolving?
So are you just asking me to imagine that I'm suddenly 20 another 13 billion years into the future? Is that what you're asking?
Yes.
So there's a couple of things. So quasars, as we understand them, they don't burn forever, right? They use up their fuel and then they eventually go dark. So the quasars that I will see today will basically have extinguished. So if you imagine I can see a quasar, you can imagine it's like a baby galaxy. I come back in 13 billion years, and now it's an old galaxy. It's grown up. It's given up its crazy days of being a young quasar, right? So that's fine. So remember that quasar I can see, which was in the universe when it was 2 billion years old, is now in the universe when it's 15 billion years old, right? So it's gotten old, etc. But my observable universe has grown, right? So the amount of universe I can see has gotten larger. So there will be quasars again 2 billion years after the Big Bang, which I can now see, right? So those quasars today, I where they are, I cannot see them, but they will appear. They'll grow out of the early part of the universe, and I will see those quasars. So I can always see quasars back at around 2 billion years after the Big Bang. They've just spent more and more time sending their light towards me, right? So that light would have traveled for, was it 23 or 24 billion years rather than the 13 billion years or 10 billion years that we've got now. So we should see the same kind of signal. But the quasars which I observe in the future at 2 billion years after the Big Bang, I will see them run even slower than I do today because the universe has expanded even more for me, right? So again, if you think about it, if I could look back and see myself, right, I would see me in the past running in slow motion. Yeah. And so that's now propagated all the way down, and essentially you're going to see the distant universe again running even more slowly than we do today.
All right. So let me try and wrap my head around the whole thing. Like, let's go back to the black hole example and the event horizon of a black hole. From my understanding is, if there's two observers, let's say I'm approaching the black hole, you're outside the black hole, you're going to see my clock tick slower and slower as I approach the event horizon of the black hole. Mm-hmm. So is this the same case, but on a cosmological timescale? So objects that are very, very close to the time when light was emitted after the Big Bang, their clocks would seem to run at an ever ever slower rate. So it just keeps growing as we approach the cosmic microwave background radiation.
Absolutely. Actually, there's a couple of effects. So yes, you're right. If I could see through the cosmic microwave background, I think Brian Cox was saying there that it's opaque. You can't see through it, so we can only see that time roughly 300,000 years after the Big Bang. So that's one thing. The other thing is, due to the accelerated expansion of the universe, there is another horizon in the universe, similar to the event horizon, and it's called it's basically the cosmic event horizon. And so what's going to happen is, due to that accelerated expansion, we're going to see distant objects essentially vanish from view. And it'll be exactly the same as what we see with something near the event horizon of a black hole. As objects approach the cosmic horizon, we're going to see them run slower and slower and slower. We will see their light redshifted more and more and more, but their images will eventually freeze and then fade into the darkness. So this is something that's going to happen in, I can't remember exact time scale, but a few 100 billion years. I think it's a number like that. I can never remember the time scales. But what's going to happen due to the accelerated expansion is that the night sky outside of our own group of galaxies is going to become black due to the accelerated expansion. Everything's going to cross an event horizon and will be lost from our view.
So it is like a black hole then in that case, because from my understanding is, objects that come very, very close to the event horizon, the light they emit redshifts so much, it goes into the radio waves, maybe into beyond the radio waves, that it becomes basically undetectable after that point. Is that correct? What on a cosmological scale?
Yes, on a cosmological scale. So looking back all the way towards the Big Bang, we would see that happening, is that wavelengths get longer and longer. This is what the cosmic microwave background is, right? That used to be high energy photons, and now it's microwaves, and it's still getting longer and longer. But said also, due to the accelerated expansion, we have this cosmological horizon, which also plays a role, and a similar effect. Same as if you fell through the event horizon of a black hole, I would see you'd be falling, but you would appear to slow down and freeze, and then fade into radio waves, and then be undetectable. This is the same for objects crossing the cosmic horizon in the universe. They would go through the same thing. They appear to freeze and then fade into nothing.
All right. So, I mean, when it comes to cosmological time dilation, what's like the biggest misconception that you think people might have about it?
I think the biggest misconception. Well, let me explain that when this story came out, I had to speak to a lot of the media, and they don't understand time at all. So it was a difficult concept to get across. I think that the misconception people have is, when you say time ran slower in the early universe, they think that if they were there, everything would be in slow motion with respect to them, without them realizing that slow motion applies to everything about them, to the speed of their thoughts, to their heart rate, and all of it. So they wouldn't see any different, right? It's not like you would be there and you'd be in some sort of slow motion movie. The experience would be the same. So I think that's the biggest misconception people have. But I'm okay with that. I mean, I teach general relativity to my honors class here, the fourth year university class, and it's clear, that getting your head around what time is not an easy question, especially if you're a journalist and have never thought about it. Then it's not surprising that it's difficult.
So I just want to ask one more time, like, if you can just sum up the whole thing, like, just what is cosmological time dilation, what causes it, and the rate of it, just so I can have one, like,
okay,
an additional audio piece.
So cosmological time dilation is this fact that when we look out into the distant universe, we see things run slowly compared to today. And the further back we look, the slower they run. And this is a consequence of Einstein's general theory of relativity. If we live in an expanding universe, what that means is that the curvature of the universe back then is different to the curvature of the universe today. And that influences the way that clocks work when you compare a clock over there to a clock here. So one of the things I really like about this is a fundamental property of the universe, right? So it's one of those things that says we do live in a universe as described by Einstein's equations. We do live in an expanding universe. And again, it's one of those great successes of 20th and now 21st century cosmology is that these mathematical equations written down 100 years ago accurately describe how our universe behaves.
Fantastic. All right. So, Dr. Geraint Lewis, astrophysics professor from the University of Sydney, thank you so much for coming.
Thank you very much.